Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be talking about the exercise where we dive deeper into the topic of stability and equilibrium. So let's jump right in. In the last videos, we found the equations of motion. And with the help of those equations of motion, we found a equilibrium position where we Q equilibrium. And this equilibrium position was found when we set Q double dot to zero, Q dot to zero, and the only variable left is our Q equilibrium. So that's how we found it. Then, of course, we can linearize around a equilibrium position where we get the mass matrix, the damping matrix, and the stiffness matrix. The mass matrix, we got it by partially deriving our equations of motion F with Q double dot. We got the C matrix with a partial derivative of our equations of motion with Q dot. And the stiffness matrix is a partial derivative of our equations of motion with Q. And all are evaluated at a specific equilibrium position. So the mass, stiffness, and damping matrix are not constant of a system. They are for every individual equilibrium position. So to check stability in the general system, we can use the linearized equation and check the eigenvalues of the system itself. And it is only stable if the eigenvalues, the lambdas, are smaller than zero or zero. If we have a conservative system, so no damping, it is enough to check the eigenvalues of k, and they have to be larger than zero. So do not confuse these parts. If we look at the whole system, it must be zero or negative. And if we look just at the K matrix, they have to be positive or zero. Let's go to our exercise. So we have the equations of motion that are here. We have our generalized coordinates that are x and theta. We see that we have a cosine here, we have sine here, so they are nonlinear. And we want to linearize. So the first step is to find an equilibrium position with the rule that we had before. We said Q double dot to zero, Q dot to zero, and what is left is our Q equilibrium. So we remove basically this whole part because we have X double dot and Q double dot, and we're only left with this part. Here we have a theta, the theta dot that will be zero, so this is gone, and we are left with Cx is equal to zero. So x in our case is zero. Here we have no theta dot or double dot or x dot or x double dot. So this equation is giving us two positions, once a zero and again a pi. So this is the first and this is the second. And this distance is zero. So now we found the equilibrium position, and now we want to get the matrices. So we get the matrix by a partial derivative with Q double dot. We get basically, let me remove, does this work? Yes, this works. So we have basically this whole matrix, because it is only dependent on Q and on our Q double dots, which is Q with just x double dot and theta double dot. So we just copy paste the matrix. And if we evaluate it at position 1 and position 2, this is our position 1 and this is our position 2. So we have two matrices and we see that both are symmetric. Then to get the C matrix, we get this part. This part comes from this term here because this is the only part that has a Q dot, in this case a theta dot. But because after the partial derivative, we're still left over with a theta dot that is set to zero, all entries are zero. And we could have known that from the start because we have no damping, no Rehanomic constraints, and no overall motion. To get the K matrix, we do the partial derivative with respect to Q, and we are left over with, let's look up here, get rid of this. So we are left with the C, that's right there. We have no X in the lower part, we have 1 theta here, but because we have a theta dot as well, this will be set to 0, and we only have to look at the theta in the second equation of motion. So we have minus mass 2 GL cosine theta. At the equilibrium position, we have this matrix for position 1, this is 1, and this matrix for position 2. Now comes the time to analyze the stability. Because we have no damping, we have a conservative system. So it's enough, and of course no overall motion, it's enough to look at the eigenvalues of k. And this is very convenient because k in our case is both a diagonal matrix. So we see, if we just have a diagonal, these are our eigenvectors. So in the first position, we have c and m2g times l, and this is all, they are both larger than 0. And in the second position, we have c, again, that is larger than 0, but then we have a minus m2 times gl, and this is negative. So we see that the second position is not stable, while the first position is stable, because both eigenvalues are larger than 0. If we then combine our linearized system, we have the matrix M and the stiffness matrix K multiplied with Q double dot and our Q dot, and this is our final linearized equation of the system at position 1. So again, these equations are only valid for the stable equilibrium position where the mass did not move and the pendulum is just hanging down. So you see that this is not complicated. If you know what you're doing, you can do this very, very fast. You just have to, again, I summarize the whole thing. You just have to get the equilibrium position, then you have to linearize, and this is all you need to do. If you want to see if it's stable or not, you can use the eigenvalues of k or the eigenvalues of the whole system, or just the eigenvalues of k itself. If you have any questions regarding these exercises, feel free to ask them in the comments down below. I will be very happy to answer all your questions. Thank you very much, and I'll see you in the next video.